Greetings, students, and welcome to today's exploration of an intriguing computational challenge, the three-sum problem, as presented in LeetCode Problem 15. Our task is to delve into the realm of integer arrays and uncover all unique triplets that sum to 0. Imagine an array filled with both positive and negative integers, such as the one provided, -1, 0, 1, 2, -1, -4. Here, our objective is to identify combinations of three distinct numbers that, when summed, yield the result of 0. For instance, the triplet -1, 0, 1 achieves this sum, as does -1, -1, 2. It is imperative that we not only find these combinations, but also ensure that our output is devoid of any duplicates. Thus, we seek to compile a list of unique triplets, each representing a fascinating intersection of mathematics and algorithmic thought. Let us embark on this intellectual journey together. Hashing with two pointers is a powerful technique that merges the efficiency of a hash table with the simplicity of the two-pointer approach. Imagine you have a list of numbers, and you want to find pairs that add up to a specific value. Instead of checking every possible pair, which can be slow, we can use two pointers to make this process faster. As we traverse the list with one pointer, we can use a hash table to store the numbers we've already seen. This allows us to quickly check if the complement of the current number, meaning the number needed to reach our target sum, exists in our hash table. If it does, we've found our pair. This technique significantly reduces the time it would take if we were to use nested loops, making it particularly useful for large data sets. By combining these methods, we simplify our implementation and enhance performance, turning a potentially slow solution into a quick and efficient one. Let's dive into the function shown on the slide, which creates a frequency dictionary using hashing. The first step is to initialize an empty dictionary, which we'll call frequency. This dictionary will help us keep track of how many times each number appears in our input array. Next, we loop through each number in the array. For every number, we check if it's already in our frequency dictionary. If it is, we simply increase its count by 1. If it's not, we add this number to the dictionary and set its count to 1. This process allows us to efficiently count occurrences of each number. Finally, once we've processed the entire array, we return the frequency dictionary. This is a powerful technique because using a dictionary allows us to look up counts in constant time, making our function efficient even for larger data sets. This technique is particularly useful in problems like three-sum, where understanding the frequency of elements can lead to faster solutions. A frequency array is a powerful tool for counting and storing how often each distinct element appears in a collection, like an array or a list. Imagine you have a box of colored marbles, and you want to know how many of each color you have. A frequency array acts like a chart where each color has its own space, and you simply fill in the number of marbles for that color. The magic of frequency arrays shines when we know the range of possible values. This allows us to count efficiently, reducing the time it takes to analyze our data to linear time, or ON. So instead of using nested loops that slow us down, we can quickly see how many times each item appears. To create a frequency array, we just go through our original collection, incrementing the count for each element we encounter. Once we have our frequency array ready, we can easily find the most common colors or see if any colors are missing. This concept is fundamental in computer science, paving the way for more complex algorithms and data analyses. In this slide, we have a function called frequency array that helps us count how often each element appears in a list. First, we initialize an empty dictionary named frequency. Think of this dictionary as a storage box where we'll keep track of each element and its count. Next, we loop through each element in the input list called elements. For each element, we update our dictionary. We look up the current count of that element using frequency.getElement0. This method checks if the element is already in our dictionary. If it is, we take its count. If not, we start at 0. Then we add 1 to this count and store it back in the dictionary. Finally, once we've counted all the elements, we convert our dictionary into a list of tuples. Each tuple contains the element and its corresponding count. This makes it easy to see the frequency of each item, which is important for problems like three-sum, where we need to analyze how many times each number shows up. Sorting in place refers to the process of organizing the elements of an array or list without needing extra space proportional to the size of the data. This means that instead of creating a new copy of the data, we rearrange the existing elements within the same memory space. To do this, we typically use a small, constant amount of extra storage, like a few variables for temporary values. The efficiency of in-place sorting is crucial, especially when working with large data sets. For instance, if we're sorting data on devices with limited memory, excessive memory use can slow down performance or even cause crashes. In-place sorting algorithms are essential in such environments, supporting tasks in everything from database management to embedded systems. At a high level, in-place sorting involves iterating through the elements and rearranging them according to a sorting criterion, like size or alphabetical order. Take quicksort, for example. It chooses a pivot element and partitions the array around it, ensuring that smaller elements end up on one side and larger ones on the other, all while using minimal extra space. This clever swapping and partitioning allows efficient sorting while keeping memory usage low. The bubble sort algorithm is a simple way to sort a list of numbers in place. Let's break down the function step by step. First, we determine the length of the array with n equals lar. This gives us the total number of elements we need to sort. Next, we start a loop that goes through each element of the array. The outer loop runs n times because we need to ensure that every element has been compared. Inside this outer loop, we have another loop that goes from the start of the array to ni1. This is important because with each pass through the array, the largest unsorted element bubbles up to its correct position at the end, so we can ignore it in subsequent iterations. Within this inner loop, we compare each element with the one next to it. If the current element is greater than the next, we swap them. This swapping process is what organizes the elements in ascending order. Finally, once all passes are complete, we return the sorted array. Bubble sort is not the most efficient method for large lists, but it's a great way to understand the basics of sorting in place. To solve the three-sum problem, we start with a key step, sorting the input array. This sorting helps us efficiently navigate the array and skip any duplicates that may arise later. We achieve this with the operation nums.sort, which takes O n log n time. Next, we create an empty list called result to store our unique triplets that sum to 0. Now we loop through the array, but only up to the third last element to ensure there's enough room for triplets. If we encounter a number that's the same as the previous one, we skip it to avoid counting duplicates. We then set up two pointers, one starting just after the current element and the other at the end of the array. As we work with these pointers, we calculate the sum of the triplet formed by the current element and the two pointers. If the sum is 0, we add this triplet to our result and adjust the pointers inward, skipping duplicates again. If the sum is less than 0, we move the left pointer to increase the sum. Conversely, if the sum is greater than 0, we move the right pointer to decrease it. Lastly, after going through the array, we return our result list containing all unique triplets that sum to 0. In summary, sorting helps us manage duplicates efficiently, and the two-pointer approach allows us to explore potential triplets in a linear manner after sorting. Overall, the algorithm has a time complexity of O(n squared), driven by the nested structure of our iterations, while sorting contributes O(n log n). In this problem, we are tasked with identifying all unique triplets within a given array of integers that sum to 0. It is imperative to ensure that no duplicate triplets are included, and the output can be presented in any order. The constraints to consider are that the array's length must be between 3 and 3000, and each integer can vary from -100,000 to +100,000. These parameters significantly influence our approach to efficiently finding the solution. The provided Python code addresses the well-known LeetCode Problem 15, commonly referred to as the three-sum problem. The goal here is to find all unique triplets in an integer array that sum to 0. This algorithm operates with a time complexity of O(n squared), which is efficient for this type of problem because we need to look at pairs of elements. The process begins by sorting the input list nums. This sorting step is crucial as it allows us to apply a two-pointer technique, which speeds up our search for triplet sums. The outer loop iterates through each element using its index I, treating each element as a potential first member of the triplet. To prevent duplicates in our results, we include a check that skips over any repeated values. Inside the outer loop, we have a while loop that uses two pointers. Left starts from the beginning of the array, while right starts from the end. We calculate the sum of the three elements at indices I, left, and right. If this sum is less than 0, we know we need a larger number, so we move the left pointer to the right. If the sum is greater than 0, we need a smaller number, prompting us to move the right pointer to the left. When a valid triplet is found, it gets added to our results, and we skip any duplicates to maintain uniqueness. This structured approach efficiently narrows down the possibilities, allowing us to systematically find all unique triplet combinations that meet the requirement of summing to 0. The time complexity of the three-sum problem is O(n) sword. This means that if we have an array with n elements, the number of operations grows quadratically as n increases. To find triplets that sum to 0, we typically use two nested loops. The outer loop picks one element, and the inner loop searches for pairs that, together with that element, yield the target sum. Each additional element in the array significantly increases the number of comparisons we need to make. Now, regarding space complexity, it is O(n). This is because we often use a hash set or an array to store unique triplets we find. As we process each element from the array, the space used can grow linearly with the number of unique elements. Imagine you're keeping track of different combinations. The more unique elements you have, the more space you need to store these combinations. This linear growth in space allows us to efficiently manage our results without redundancy.